Okay. Hello, everybody. Welcome back. So this is the second part of our lecture on UV astronomy by Kyle Cook. And with that said, I give this over to Kyle.
All right, then, yeah. Thank you all. Welcome back to everybody who was here last week as well. And I'll just kind of jump right into this, where today is the planned kind of science part of the talk or the series. So, last week, of course, was kind of the history change, thank you, was kind of the history and why we should be caring about this and everything that's going on. And this week is, of course, the science cases. Um, I kind of left last week with a few thoughts, one of which was, is there an interest or a need for UV? And I would definitely say the goal of today is to convince you that there is both. And to that end, I wanted to start with, oh, yeah, I added that. I wanted to start with this kind of excerpt from a as yet unreleased paper that's part of the HWO group. I did get permission to share this from an unpublished work. Um, and the main part I kind of want to draw to here is right around here, starting with the nearly all of the science cases. Because what they did is they took the 60 earliest science cases that were proposed for HWOs and just looked at what was needed. And as they say here, nearly all of the science cases require UV wavelengths. Um, I do think nearly all is not super clear. Is that missing one or two, but it doesn't say. And as I said, this is a paper. And of those 60, 25, so nearly half of them are asking for observations at shorter than 100 nanometers. So, more blue. Of course, they're asking for near UV as well. So kind of the full range here, but kind of the interesting thing here is, if you ask the science community, if we have an instrument that goes from UV to infrared and covers that wide wavelength range, or near infrared, I should say, um, what wavelengths do you need out of that? What's important to your science? And virtually everybody said they need UV wavelengths, at least everybody that responded early. So I think without going any further, in my mind, that addresses the interest, right? There is absolutely interest from the community to have UV wavelengths, even short word or blue word of 100 nanometers. So more into that extreme UV range. Um, but the question remains why? Why would there be such an interest? And largely put, the UV is really telling us something about our most energetic our ionized, our hot regions of the universe. So areas where we have largely hot ionized gas. UV is great here. Which hot ionized gas? You have stars. You have that in galaxies. AGN doing a lot of the work there. ISM, IGM, everything else. And we'll talk about some of these concepts kind of as we go. But definitely the thing that I want to point out kind of loudly here is that what I'll talk about today is certainly not complete. Any one science case could be a entire, 45-minute talk. So I'm definitely not going to touch every possible case for UV. I will, and each case that I touch is not a comprehensive look of that because, again, each case could be a 45-minute talk or longer. So really my intent is just to give a bit of the idea, a bit of the, as I say here, the flavor of what these science cases are and why they're important. So if your favorite science case didn't make it into this, I apologize, but I would love to hear what your favorite science case is. So, all right. And then jumping into the first case here. Sorry, my computer keeps switching screens or something. Okay. So let's go back to our favorite scientific fiction, the Bohr model of the atom, and kind of characterize what we're talking about when we're talking about UV, at least in some cases. So, as you have probably all seen at some point, you have your positively charged nucleus, orbitals around the outside, an electron at some orbital, and that electron can simply drop to a lower orbital, emitting wavelength emitting a photon with a wavelength corresponding to the Rydberg formula here. Probably nothing new to you all here. Um, the ground state, any transitions into the ground state of neutral hydrogen or out of the ground state um, correspond to the Lyman series, and every single one of those transitions is a UV wavelength. And if you recall the kind of definitions that I gave of different UV bands, different UV um, ranges last week, there I kind of noted this weird why one was at 91.2 nanometers, and this range is what we had defined as the Lyman UV. So that is the range where you are getting these UV transitions from the atoms here. So this is an interesting region, and it is what leads us to a very important concept right out of the gate of something we call the Lyman break. So if you think of what a galaxy looks like across all wavelengths, you might get something like this. So I'll talk about it more later, but we're going to call this a galaxy SED. And just kind of for reference here, this model that I generated would be a Milky Way mass galaxy at a redshift of 0, so right on top of us, with a pretty simplistic modeling. But what I wanted to highlight is you've kind of got all these wavelengths, a lot of things going on, and then this very, very sharp break right at 91.2 nanometers. Sorry for the unit change. I kind of noticed that after I did it, and I just being lazy, didn't want to go back and rerun the model. Um, sorry. So you get this break right here. And what happens here is when your atomic hydrogen gets completely ionized. So you have completely kicked the electron from the ground state out into the surrounding environment. So now you've separated those two out. So once you go blueward of 91.2 nanometers, you have completely ionized hydrogen and you're no longer getting those neutral hydrogen transition lines. So you see this stark drop here because, as we all know, hydrogen is the most abundant element in the universe. So once you remove your signal from hydrogen, you get a pretty stark decrease there. Um, I mentioned here it's highly characteristic of star-forming galaxies. I'll show that here in just a few moments. But it also provides a pretty interesting way to estimate the redshift of a galaxy, because I think one of the first lessons we're all supposed to learn about astronomy is distance is hard. So what we can do is obviously as we redshift items or as things move further away, the spectrum redshifts. So as this gets further away, this entire feature will move more and more and more towards the red, depending on how far away it is. So if we observe a galaxy in multiple bands, so for instance, H, J, Z, I, V bands, where this is our optical, this is getting us towards infrared, and then we've kind of got some near infrared bands here. Um, you can see this is probably a good one here. Obviously something there in the H band, obviously something there in the J band, maybe Z, and then all of a sudden you start looking and there's nothing there anymore. So these are what we call dropout galaxies. And we'll refer to them. So we may say it's a J dropout or an H dropout or some are different depending on where they are. But this becomes a selection technique where I want to look at galaxies at a specific redshift range. And so I'm going to look at those that drop out between two specific bands, giving me a general idea of what redshift and therefore what distance these galaxies are at. Um, we did this early with optical. And then as we improved our infrared and UV, we've been able to take where we were, those red shifts, 3 to 4, and broaden it out in both directions. Um, James Webb is doing the exact same thing with distant galaxies. It's still the UV light. It's just been shifted all the way over into James Webb's bands. Um, so that far infrared becomes a way to look for the Lyman break at these in distant galaxies. But we can also do the same thing with more nearby galaxies by staying within the ultraviolet itself. So it's all ultraviolet light just being observed in different bands as that light is redshifted to different bands. Sorry, I'm going to interrupt myself here for a second and just say one thing I didn't say last week, but should hold is if you all have any questions, please feel free to interrupt me. Just jump in. I may not see a chat window, so if you have a question or I say something that you think you're not following or you don't understand or just you think I've completely lost my mind, that's possible too. Feel free to jump in. All right. So actually, let me just kind of, since I interrupted there, just kind of wrap that idea up. Is this idea of using this Lyman break, that moment when your neutral hydrogen gets completely ionized, is an effective way to select galaxies and estimate redshifts. Jumping to a little bit of a different topic here is the idea of going back to Wien's law, looking at galaxies or looking at stars as black bodies. Just a quick reminder of things here. Our hottest, most massive stars peak right here in the UV, where actually our UV, if we define at 400, is kind of this whole range here. So we get peaks in the UV for our most massive stars. If you actually zoom in on these, you can see these lower models are peaking outside the UV. The problem is the intensity goes up, the spectral radiance goes up so quickly that your, you know, cooler objects get completely dwarfed. Um, but your most massive, your O stars, your B stars, even into A stars are peaking in the UV. And your massive stars are your hot stars, your young stars. So the UV portion of that galaxy SED we looked at is heavily influenced by young stars. So, for instance, coming back here, I gave this model in particular a very recent burst of star formation. So you see this heavy UV increase leading up to that Lyman break. In this case, I was just trying to emphasize the Lyman break, of course. Um, there is an additional point here, this idea of outshining, because our massive stars are so much brighter that what happens is when we're looking at galaxies, distant galaxies, and we want to understand what's happening with stars to pick out all their stellar mass, we can't really see the light from the less massive stars, the fainter stars. We just get completely blindsided by the massive stars. So it actually makes our modeling much more difficult, this idea of outshining. But the UV in particular is dominated by those young stars, those heavy, massive stars, and to the point of almost exclusion of our low mass stars. The reason I bring all this up, oh, actually, I wanted to go in a little bit more on the spectral energy distribution, where these are, as I said, the galaxy's flux over wavelength. I apologize, this should be the log of the flux right here. This is a logarithmic scale here. And most importantly, what it is it's like this is a fingerprint on every model, every process, every parameter that goes into a galaxy. So if you change the amount of dust, this model will change. If you change the amount of metals, What's the metallicity of this galaxy? Then all of a sudden things change. So they're quite different depending on what happens. And you can see that's not what I wanted to do yet. Accidental click. You can see in this case, I just chose this 5 gigayears. But for reference, um, sorry, this is being super sensitive today for some reason. There we go. So just kind of um, different galaxies over, or an SED kind of over. What I want to be clear on is what I am not doing here is evolving a single galaxy. Okay. This is not one galaxy over time. This is basically the same galaxy. All the parameters are exactly the same, and the only thing I'm changing is the age of its last burst. So a couple interesting things pop out to us. First, if we go to our very early one, basically straight slope down, you notice as it gets older, you see a lot more spectral lines coming up. That's not too surprising if this is when the galaxy first turns on, and then over time, it's enriching its environment by having stars, fusing heavier elements, going supernova, and distributing those elements across the galaxy. So you see kind of the emergence of spectral lines as we go to a higher star formation age. The other thing I want to point out here is that you see this significantly changing the relationship where we go from basically negative slope all the way through the UV ranges to an overall more positive slope as our more massive stars die off. So there is a value called the UV beta, which is basically just the slope if we're in a log space. So it's a power law, but if you go logarithmic in both spaces, you can fit that with a linear relationship. And the points I've chosen here are the band passes that correspond to the Galax, excuse me, the Galax telescope, where you just have two bands, a far UV and a near UV. Something like this galaxy here at a 4 gig a year since its most recent star formation burst is going to give this very negative, very blue slope. Whereas at 8 gig a years, you start seeing a much more positive, much redder slope as those massive stars have died out. This kind of starts touching on a lot of my research. Is obviously you can see there's more details going on in here. What if we sample not over these 2 points, but what if we sample over more points kind of distributed within this range? Does that tell us more? Can we narrow that down a little bit? What does that tell us about our most recent age of star formation? And if you were at the KAAS in the spring, this is some of what I talked about and basically showed that Galax doesn't do a great job of constraining the age, but other instruments like Swift, which take this more narrow range here and break it down, actually seem to do a much better, constrain that star formation age a lot better. Um, so kind of wrapping up the ideas of star formation, I'm desperately trying not to spend too much time here because it is my research and I get really excited. Um, the UV is containing a lot of information about the recent star formation history of galaxies. And in particular, one thing I didn't mention, fitting SEDs to galaxies is notoriously not fantastic at getting accurate star formation histories. Kind of one of the arguments of my current research is if we had better UV information going into our SED fits, then we may be able to do a better job of recovering a more accurate star formation history. Seems like a reasonable connection. Um, and you can look for my upcoming papers to hopefully talk about that. And as I say, that's not a shameless plug at all. Don't call me out on it. Um, I kind of jump into the next science case here, I felt as if it would be incredibly wrong of me to not talk about AGN, considering how many AGN folks I know are in the KAAS area here. So I think at the KAAS meeting, I probably saw this figure along with different variations many times. So some people on here may be like, hey, that's the one I use. But just a quick statement on what an AGN is, where you have at the core of a galaxy your supermassive black hole. It is actively accreting material from your little accretion disk hiding in here. And behind its obscuring torus, you get these jets of radiation, very energetic process coming out, arcing, arching way beyond the bounds of the galaxy itself. So this little solar system size thing is outputting an incredible amount of energy, which again, going outside the galaxy means it has incredible interactions with the intergalactic medium, or just otherwise, that stuff that's in between galaxies. We think of the IGM as being this very diffuse area, which it is, but it contains about half the baryons of the entire universe. Um, and for those of you who may be, taking some physics classes, yes, astronomers use baryons very lightly. That includes things like electrons and everything else. It's basically everything that's not all the matter that's not dark matter. Don't tell your particle physicist friends; it drives them batty. But yeah, so by baryons, we are meaning everything that's not dark matter, basically. So half of the baryonic matter of the universe is hiding out in this intergalactic medium. So it's obviously a really important thing. And galaxies don't exist as closed systems. In fact, they interact with the intergalactic medium quite a bit. So we want to understand that IGM and AGN can act like a flashlight shining through the gas clouds of the intergalactic medium on its way to us. So you can get these really interesting spectra out of the light. Or actually, let me back up and say this a little bit differently. What we get is the kind of backlit spectrum of the AGN, the quasar itself, but superimposed on top of it is all the information about the IGM that it passed through along the way, which means we can study that IGM within the light of quasars, within the light of AGN in general. So I definitely want to point out here that this should look like an absolute mess to you. If it doesn't, then you have done more spectra than I have. This looks absolutely messy, and it's actually what we end up calling the Lyman alpha forest. So when you come to these kind of terms, what you've probably run across most is like hydrogen alpha, which is that Balmer transition from like from 3 to 2, or principal quantum number 3 to 2. But Lyman alpha is just your first transition in the Lyman series where you're going from 2 to 1. So here you have, or in this case, it's an absorption, so you're going the other way. Um, so what you get out of this Lyman alpha forest, what you're actually getting here is the light from the AGN as it's shining through the IGM clouds at different redshifts. So you kind of get Lyman alpha across this broad band of range of redshifts as it travels through the universe to us. I found this great animation, which I kind of thought was going to start at the beginning. But as this spectrum redshifts, here we go. As the spectrum redshifts, you continuously get these Lyman alpha lines showing up as it's passing through different areas of the IGM. And if you do spectra, you have way more patience than this poor photometric guy, but you can dig through this forest and start pulling out other UV lines. Um, Carbon 3 and 4, silicon 3 and 4, oxygen 6. These lines telling us something about the composition of the IgM that it's passing through. It's worth taking a quick moment here to pause, I think, and just point out this notation in case anybody here hasn't seen it. This is in my opinion, a terrible notation. So like carbon 3 is doubly ionized carbon. So it's carbon that we've kicked 2 electrons off of. Carbon 4 is triply ionized, so we've kicked 3 off. Then you have something like oxygen 6, where we've actually heavily ionized, kicked 5 electrons off of that. So, you have to do a little bit of math. It's -1. I think we can all handle that, but I think we could have done better too on the notation. I wasn't asked, I wasn't alive. Um, But the point here is the idea that we can actually search through this Lyman alpha forest and start understanding what kind of elements are in the IgM over time, which this is important because it tells us the chemical evolution of the universe. It tells us how we went from a universe that was mostly hydrogen with a sprinkling of helium into the complexity that we see today, which is still mostly hydrogen, maybe a touch more than a sprinkling of helium, and then, just a dusting of everything else. But it's that everything else that gives us, life, Earth, everything that we need, the carbon that makes us up. So understanding that's kind of a big deal. So, kind of trying to, again, wrap those ideas up is the idea that, again, this is half of the universe, basically, half the normal matter of the universe, and it informs so many different areas. Um, it's also, um, yeah, that's kind of what I said. Sorry, but it goes through and it just reveals those highly ionized species so that we can understand the makeup of the IgM over cosmic time, which is, again, vastly important. All right. Then I'm going to jump all the way over to something much smaller scale, exoplanet habitability. I felt this was a topic we had to kind of touch on, being that this is Habitable Worlds Observatory that's coming up. So understanding why we or what the UV gives us for habitable worlds is definitely a starting point. And there are more science cases in habitable worlds or exoplanets than this, but where I wanted to start. So we think of, again, we go back to stars in general. Massive stars, we're probably not going to find any kind of intelligent life around an O star just because those stars don't live long enough for for planets to form, life to form on planets, and then life to evolve to a point like we are now. The star is going to go supernova and wipe out anything in its area long before it gets to that point. So there is kind of the question is like, well, what if we go to the lowest mass stars because they're going to live essentially forever? Um, so what about them? Those should have very stable environments. So we look to M stars. Um, they're very long-lived and they might be a good target for habitable planets. However, M stars come with their own challenges. A main one is they are prone to extreme UV flares. Um, so despite their black body peak being nowhere near the UV, they still put out a lot of UV radiation in very violent, dramatic bursts. So the question arises, could a planet survive around an M star? Or does the environment or does the atmosphere just get boiled off, cooked off, and everything killed, before you can develop, before you can actually survive and evolve? So, kind of interesting point here on what the UV is actually doing for us or to us, right? We talked about like UVA, UVB, that makes it through. You kind of makes it through the atmosphere. You start filtering it kind of UVC, near UV ranges. But in particular, I want us to look at the extreme UV here because what the extreme UV does very, very well, actually, is it heats the upper layers of the atmosphere. So you've got the atmosphere around your planet, it heats it up, it swells up, it injects energy into that. because, right, our thermal energy is just kind of random motion of the atoms, of the particles. So if you heat that up, all of a sudden the random velocities of your particles speed up, which means they can escape. If they're right at the edge of being able to escape the planet, and then all of a sudden you put more energy into them, then your atmosphere just kind of starts escaping off into space. So the question becomes, these UV flares from M stars, are they strong enough to basically, I'm going to call it boil off the atmosphere, though boil's maybe not the right term here, but does that inject enough energy to start having the important things that you need escape the atmosphere of the planet? And does the atmosphere just kind of disappear? Um, the other idea is down here in the far UV, where this is where your far UV is what's actually really good at helping form your ozone. Because you can have your molecular oxygen, two oxygen atoms bound together there. Your far UV comes in and then it splits them apart. And when it splits them apart, then they can go um, join, these two oxygen atoms. Sorry, I kind of got lost in my thought there for a second. These two oxygen atoms can go find a different molecular oxygen and join up. It's the near UV and your UVC ranges that actually do a more effective job of breaking the O3 itself. So basically, near UV is helping break down your ozone. Your far UV is actually helping form it by breaking the molecular oxygen down and making free oxygen to bond. So all this to say, the question here becomes, what is actually the UV environment of M stars? And there are problems with doing that. There's some technological hurdles. There is also extinction issues. Um, but we do have a subset of M stars that would be great to observe. But there are no extreme UV instruments capable. If we go back to this table that I shared last week, right? Um, Spear was the most recent, but that's the one that didn't last hardly any time at all, less than a year. Everything else, nothing reaches really down into that extreme UV range. Um, so, which is kind of our, let's call it 10 to 90 nanometers. So nothing, we have no instrument that can actually observe those environments. So astronomers are trying to be creative and trying to do other things and find ways to get around that. However, the direct detection of the UV environment around M dwarfs would really help us answer for certain, can a planet actually survive there? Can an atmosphere remain bound to the planet, or does it just completely get lost and swamped out? Um, and there are, again, numerous calls, as we saw at the very beginning, numerous calls for HWO to include wavelengths bluer, more energetic than the 100 nanometer mark. Um, Another thing I kind of want to point out is we always talk about habitable worlds, and then in the back of our mind, I think we're translating that to Earth-like worlds, right? But even taking that, um, Earth is not the same over time. So, you kind of have in this figure here this brightness of the planet of Earth across different time frames. So here's a very old Earth, or actually, let me say a very young Earth, long ago, when life is beginning to arise. And you can see that what this looks like is very different than today. In fact, one of the interesting things, what they're calling this Archean haze, is kind of a direct result of life. Can we observe planets that have this kind of haze? And if you look, it's down here in the UV where this makes a big difference on whether the haze exists or it does not. So we can start seeing, are these early precursors for life? Um, Again, no instrument that we can do that with right now. But if all of a sudden we're able to do that, then we can start looking at not just does this planet have water, for instance, which is a common thing we talk about today, but does this planet have the same type of early life characteristics that we have here on Earth, that we had here on Earth? So, yes, there may be very non-Earth-like planets, but I think it's important to say right out of the gate that Earth-like does not mean the same thing over time. Earth-like is very, very different at different stages in Earth's development, and all these stages include life. So, just kind of a quick aside on that, that I wanted to point out. So, kind of additional projects that can be done. I have to talk a little bit, even though I said I wasn't going to do this as a full thing, this idea of LAMP right here, because this is an instrument that's on the Lunar Reconnaissance Orbiter, and it is the coolest thing in the world. This is just incredibly interesting to me because what this is the Lyman Alpha monitoring project, and it is looking for the signal of from the permanently shaded regions of the moon. So those regions that never see sunlight. But we stop to think, okay, then what is it seeing? Because if it's not getting sunlight, then we're not seeing reflected sunlight. But we're not going to be seeing Lyman alpha emission from these incredibly cold areas. So what are we actually seeing? It is looking at, and if you all don't find this as cool as I do, I don't know what to do. It is looking at the reflection of distant stars off of the moon, not the sun. It is looking at the reflection of stars off of the moon. That incredibly faint signal, and that it is doing that, and it's entirely a UV instrument, is incredibly cool. Um, so when you see a lot of these studies about the permanently shaded regions of the moon, this is the type of stuff that's being done on that. Um, The other ones I've listed here are all proposed science cases for Habitable Worlds Observatory and the wavelengths that they're requesting. You see a lot of them are asking for kind of extreme UV or right at the extreme UV ranges. But looking for life on exoplanets, looking at AGN-driven outflows, specifically looking for ocean worlds, energy extraction from black holes, ISM properties, the interstellar medium properties with UV-IFU. All these things are proposed, and at the end, I actually have a link where you can go see kind of all these proposed projects as well. Um, I do want to point out a couple challenges with UV because I think it would be incredibly unfair of me to not mention them here. One thing in particular is astronomical dust is incredibly efficient at absorbing UV light. So if you think back to our spectral energy distributions, that UV slope is dramatically changed by dust. So you really have to take dust into effect to do this. The last week I mentioned, a look of the galaxy through or a UV look through the dust of the galaxy would not be a particularly interesting picture, and that's because all the UV light's basically going to get absorbed by that dust. Um, it does get re-radiated as infrared, which then you get this incredible connection between the UV and the infrared. And in particular, that beta slope we talked about has a connection to the infrared as well. So, these are important things. I think it's incredibly important to point out that the absorption of UV by dust is a massive um, limiter and a hurdle that we have to always take into account with our UV science. Um, Day two thoughts. I think I wrap up day two. My first thought is I can't believe I took less time than I did with the history because I thought the history was going to be quite short. So, but the main idea, I hope I have convinced you at least that there is interest and need for UV data. because the research opportunities span far, far more than I talked about today, and I tried to do a pretty wide swath of topics here. I would also throw in, if you're ever curious, you can go to the Space Weather Prediction Center at NOAA and look at the sun images they have. They're all UV images. A lot of them have the wavelengths at the end. The UV is very, very good at showing kind of these fine features, these spicules and everything else on the sun. You can see it exquisitely with UV. Um, so um, there's definitely a lot of stellar things to do. Cometary science. UV is great for studying the kind of outgassed material from comets as it approaches the sun. Again, this kind of hot, violent experience. You can kind of take spectra of that and see what's going on kind of in these cometary nuclei and things of that sense. Um, Down here is both a link and a QR code to the HWO Science Case portal where all the current science cases are public. So you can go look at those and see what people are looking at, find your favorite and kind of look through and see what people are talking about and what they can do with the science. So I will actually wrap it up there, and I'm happy to take any and all questions.
Kyle, thank you. Um, yeah, I'd had no idea about the LRO detector, the one that looks for the starlight. I mean, I'm familiar, of course, through Lunar Ice Cube about the permanently shaded regions to look for water ice, but that's wow.
Yeah,
Um,
I ran across that. I hadn't heard of it either, and I ran across. I was like, hang on, wait a second. I have to think about this because I can't. I'm like that faint of a signal, and I got down a pretty deep rabbit hole on a NASA site of them like, yeah, it's basically the background radiation from all the stars, and that's what's being reflected, and that's what they're looking at.
no, actually I do believe it because if you have ever been to a very dark site like McDonald Observatory, you have a new moon night, and you see shadows. You see the shadows from the
Mhm.
starlight,
Yeah,
or the shadows from the Milky Way. So I do believe that that's possible. Um, but you have to be at a very dark spot. Well, and if you're at the permanently shaded region of the moon, you are.
right.
I mean, how much darker can you get, right? I mean, wow,
Yeah,
that
though I did
is.
find it interesting. They said that they also they take these observations also during the on the light side of the moon. You're still looking
Hmm.
at a permanently shaded region,
Yes.
right? So that may just be a field of view where they're able to focus in that narrowly and block out the sunlight. But just yeah, I thought that was an incredibly cool point.
Hmm. Yeah, that's very cool. Yeah, I hope everybody is convinced by this because this has been always our problem in the past, right? Convincing people to do UV observations because uh, there are only right now, what, how many instruments in space, HST, Swift, and the OM on XMM, uh,
Yeah.
and Astrosat in some
Yeah, I was
respect,
going to
right?
say Astrosat, I think is still operating as well.
Mm-hmm.
Um, but yeah, it's not much. And I think kind of the joke I've heard around is, it's like um, HST is a UV telescope because, well, we really had no choice. It's that wasn't the idea. You
Yeah.
know? Um, so we've got some
It's
we've got some UV filters on it, but they're yeah, they're not really what we would want.
mm-hmm. Yeah, it's we there is really a need for, and what you said, you need an EUV mission like Fuse 20 years ago.
Yeah.
That really goes into the extreme ultraviolet. Because I'm coming more from the outflow side in this respect. When you look at broad absorption line quasars, now broad absorption line quasars typically, you shift it to, you have the redshift and you can observe them in the optical. But there are a lot of nearby sources where we would like to see more UV observations, AGN
Mhm.
with with far UV observations, nearby sources that we could study because they are simply brighter. So you simply get more information this way.
Yeah, and when we think about, because what we do in astronomy, right, is we don't watch an object evolve over time. We find analogs at different times, and we've gotten pretty good, I feel like, recently in finding our analogs further and further and further out.
Hmm.
But we need those nearby analogs as well. And
Yep.
that's really where the UV lives, is kind of that nearby before you redshift beyond the Lyman break.
Right. Yeah.
Um, so yeah, we need our nearby analogs as well, because that's ultimately the end state that we're trying to find for our simulations and things of that nature.
Hmm.
And if our simulations don't even fully understand the end state we're getting to, it becomes hard to compare and say this is actually matching what we're seeing today.
Hmm. Okay. Any other questions for Kyle? Okay, well, then thank you very much. I will see everybody back next week. Again, we will post this, of course, also on our website. So I need to talk with Charlie about that, but we will post it. So if you can rewatch it, and and then next week you will be talking about the instruments.
Yeah, we'll move to the instrumentation side of things and kind of where we are, where we've been, where we are, and kind of pushing a little bit into where we're going with it. So,
Okay, super. Thank you. And I will
all right.
stop the recording here. Thank
All
you,
right.
everybody, for being here today. Bye.
Thank you.